We'll get started in a couple of minutes, but I just want to tell the speakers that are in the room to please stick to your time, because unfortunately I will have to cut you off if you go too long. First, welcome everybody to the next session of Functional Composite Materials. It's almost time. Our first speaker is Fabian Schwett from Kiel University in Germany. Hi, Fabian.
Hi.
Feel free to share your screen.
Yeah. Let's begin. So, should be fine now?
Yep.
Oh, okay. Nice. Yeah. Then I go ahead. Yeah. I'm happy to be here today and starting this session, giving the first talk here. My name is Fabian Schwett. I'm from Kiel University from Germany. And today I want to show you some of our work we recently did on multiscale material system from low-dimensional nanomaterials such as graphene and hexagonal boron nitride. So, I mean, most of us are here because nanomaterials have fascinating properties. And for a lot of applications, it is, however, important to bring these properties also to the macroscopic scale, for example, for energy storage devices, fuel cells, photonic cell scaffolds, and also polymer composites. So we want to go from the nano to the macro scale. And today I want to show you a little bit what is our approach and how we can use then these materials to create also new functional composites. So our approach starts with this white powder we synthesize in our lab. This is not the classical white powder you might know from your lab because it's consisting of tetrapodal shaped zinc oxide microparticles. We are synthesizing with a flame transport synthesis. And what we can do now with the help of these particles, we can take a small amount of these particles, place it into a mold, compress it slightly, sinter it, and what we end up with are network structures consisting of these zinc oxide tetrapods. You can see on the photograph here, we can prepare different network structures, different sizes, different geometries. But what they all have in common is that they have a porosity on this photograph of 94%. And actually, we can also tailor this porosity. So we can tailor it between 50 to 98%. And this is one of the most lightweight ceramic network structures and lowest density ceramics you will find also in literature. You can also see this in the FCM. So you can see this random arrangement of tetrapodal shaped particles, all randomly arranged in 3D space. You can also see this high free volume of our structure. And if you have a closer look, you can also identify some sinter bridges. So we sinter these particles together to really obtain one network structure, not just a loose compound of particles. So if we have even a closer look, you can also see surface can be quite rough. But actually what we use now these particles for, these network structures, we use them as a sacrificial template material. So what we developed in the past are different processes to coat these structures now with a very thin layer of nanomaterials. We can do this by dry chemistry, so CVD processes, for example, or wet chemistry. Afterwards, after the coating, we etch away the zinc oxide, and then we are left with a freestanding thin film in the form of hollow microtubes. And these microtubes are all connected to each other. And this makes it now possible to have this nanoscopic scale on the macroscopic scale. So just to show you an example, this is the aerographene we are producing. So this network structure just come out of graphene. It looks like we do it with a CVD process, but actually it's done wet chemically. And you can see the sample on the left corner. and you see this network structure of these hollow microtubes. And on the top right image, you see also that these tubes have a very low wall thickness because you see the next tube behind it. So these structures are now multi-scale material system, right? We have macro scale, and then we go to the microtube. So we have on the micro scale with a length of like 25 micrometer. But these tubes have a nanoscopic wall thickness, and this enables us to use here with the help of these materials some special functions. We are talking about materials with densities well below 1 milligram per cubic centimeter and a porosity of 99.99%. So it's different to what you know, for example, for aerogeels. Aerogeels have a higher density and a lower porosity. So, and actually we can now use these materials to bring this nanoscopic functionality on the macro scale. And I will show you now what we can do, for example, with the aerographene. So as I mentioned, I showed you the SEM image. We produce this structure wet chemically. So the process is quite simple. What we do, we have here the template, and then we just drop the nanomaterial dispersion onto the template. And due to the properties of the template, we get a homogeneous coating. If you want to know more details, you can have a look in our publication here. Afterwards, we etch away the zinc oxide, and then we obtain these network structures. And due to this multi-scale structure, they have fascinating mechanical properties, so we can compress them and they will come back to their original shape. This depends also on the material we are using. We can use exfoliated graphene, reduced graphene oxide, and we can also tune the density of the networks to tailor the mechanical properties as well as the conductivity. In the case of conductivity, we can reach up to 100 Siemens per meter. And this is because of the high quality also of the exfoliated graphene we are using. Actually, we get this from our collaborator, Professor Xinglang Feng from the University of Dresden. So what can we use these materials now for? I forgot. We can also upscale for some industry projects, which is not easily possible with CVD processes, but with this wet chemical approach, it's easily possible. What we can now use these structures for is we can use them to create motion. How is that? How can you see that here in the video? So you can see here an aero material, which is electrically connected. And now we apply a very short power pulse to this material, and you see the syringe is moving upwards. We can even place a weight now of 2 kilograms on top, and then we can lift this weight of 2 kilograms with a material with itself having a weight of like 10 milligrams. So what we do here, or what we call this process, is electrically powered repeatable air explosions, in short, EPRE, which we just recently published as well. And this process, you can see here schematically on the next slide. What we do, well, we have a material which basically has a very low volumetric heat capacity. So if we apply a power, even for a very short time, we can heat it up to like 400 degrees C in just 1 millisecond. And thereby, we do not only heat up the material itself, but also the gas inside the material, which, for example, can be air. And if you know your thermodynamics, if you heat air, you have a volume expansion, of course. And if you do it very fast, you can also say it's an explosion. Also, because we have this low volumetric heat capacity, the material also cools down very fast again in like 200 milliseconds. So we can repeat this process several times per second. You can actually see this here. You see we apply a power pulses of 10 milliseconds. In 1 second, we can heat the material between 120 degrees C to 400 degrees C, like 6 times roundabout. We can even be faster depending on the difference in temperature. So just to show, we can build actuators out of this, which have, in comparison to other actuator systems, for example, high power density, but also a high volumetric strain. We can also use this, for example, then for soft robotics, this could be interesting, but also for microfluidics. You can also use it, just to give an example, to create a pump, which has no mechanical moving parts, for example. So you have an aero material inside a chamber, and then you pulse it, and you can move this droplet, for example, in a defined manner from the left to the right. And of course, you can also switch on and off and so on. So just to give you an idea what is possible with this process. Well, we do not only produce materials from graphene, we can also use the white graphene, the boron nitride. This was a collaboration with the University of Cambridge and the Imperial College in London, where we produced the same structure basically, but from hexagonal boron nitride. So as you can see on the photograph, we get different properties. It's like a translucent material. And if you have a look at the SEM, you can also see again this random structure of hollow boron nitride microtubes. Surface can be quite rough. I think I have to hurry a little bit. So this system basically shows, or is a very special photonic system. It's a disordered system where we have feature sizes when we are talking about the wavelengths of visible light, which are much smaller than the wavelengths of the visible light. The thickness of the wall thickness of the tubes in the order of the wavelengths of the visible light, and lower than and much larger than the wavelengths of the visible light. But actually, this is the most important point here, this low wall thickness of the tubes, because thereby we have Rayleigh type scattering centers, which are distributed in a random fashion in a 3D structure. And this actually gives us the properties of like an artificial solid fog with a very, very high scattering strength. And why is it useful, or where is it needed? Well, you can, for example, use it to scatter laser light in a very efficient manner, because the structure itself does not absorb any light or almost no light. And then you can use it to scatter this directed laser light homogeneously in 3D space. We could show that thereby we can use this as a laser light diffuser for high brightness applications, because it withstands very high laser intensities. You can mix different colors together. And the most important point here, you reduce the speckle contrast, which is the typical feature of lasers as well. So, well, I just showed you now two kinds of materials we are producing, but actually we have more. We have also gallium nitride, for example. We can do this from MX seams, from different 2D materials. We can also use polymers, for example, by the help of an ICVD process, and so on. So we have a broad range of these materials, and all with a unique set of properties, of course. And actually, in the beginning, I showed you we want to build this structure, which is quite colorful because we use different materials. What I showed you is quite a dark structure. I just showed you one material, but we are working currently also on preparing such hybrid multi-scale material system, because then you can add different functions into one structure and use it for new functional composites, for example. So in the end, I want to thank the group I'm working in as a research group leader, as a functional nanomaterials group in Kiel, and also my PhD students, Florian and Lena, who did most of the work I just showed you, as well as the collaborators, and of course the funding. If you have questions, you can ask me now. You can also write me an email, of course. If you have ideas for collaborations, I'm open. Yeah, thank you very much for your attention, and I think I'm in time.
Thank you very much, Fabian. That was, thank you for fitting into the time. I appreciate it. And also just a beautiful talk. We have time for questions if anybody else, I don't see any chat questions, but if as people come up with them, if I may ask, in your first beautiful, I believe, SEM structure, there looked to be some kind of stratifications between the sintered points, whereas on the boron nitride later on, it seemed a bit rougher, and I didn't see the same EM stratifications. I was wondering if you could just comment
I think
on that.
what you mean, sorry.
No problem.
This is, I think what you mean is with the zinc oxide
Exactly.
here.
Yes, yes,
This,
that layering between the nodes.
Yeah, you mean this rivels.
Yes, yes.
Yes. This depends a little on the synthesis process we are using for the zinc oxide and on the pre-treatment of the structure. Actually, if you use a wet chemical process, you can also see that we are adopting these rivels. With the boron nitride process, the reaction mechanism, because it's a CVD process, it's a high temperature process, it's a little bit different, and thereby also the surface structure is a little bit different.
I see. Yeah. Got it. Thank you very much. Thank you again for that.
You're welcome. Thank you very much.
Okay, so our next talk is by Xiaoling So from National University of Singapore. The talk will be titled Pathway to Intelligence, Using Stimuli Responsive Materials for Constructing Self-Powered Autonomous Functional Systems. I don't see Xiaoling So in here. If you could share the talk, I believe we have a recording.
Hi, my name is Xiaoling. I'm from the National University of Singapore. In this presentation, I'm going to discuss how we can use stimuli-responsive materials for constructing self-powered autonomous systems and incorporating intelligence into materials. There are currently two main types of intelligence systems in our world right now. The first involves the biological systems, and the second involves the artificial intelligence that are based on electronics. These intelligence systems are very versatile, and we are now seeing a vast range of applications being developed from these systems. However, the man-made electronic systems have their disadvantages, and that include being incompatible to certain environments such as the human body for biomedical applications. And of course, that includes the very important field of drug delivery. And therefore, there's a need to extend the concept of intelligence to materials in general, and not just for electronic-based systems. Before we look at how we can incorporate intelligence into materials, let's look at the definition of a primitive form of intelligence. That can consist of three main elements. The first is to sense the signals from the surrounding environment. The second is to analyze that detected signal. The third then is to respond to the surrounding in a logical manner that is dependent on the analyzed detected signal. Here we have a good example of a living cell that may involve the sensing components, the analytical functions, and the practical functions. So how can we incorporate intelligence into materials? Here we have previously published this review article where we discuss the use of stimuli-responsive materials for constructing the intelligent materials. Stimuli-responsive materials are used because they are able to sense the signals from the surrounding environment. And in addition to that, they can also use the stimulus as the power for driving the operations of the functions of these materials. And after reviewing the many different types of functions developed from the stimuli-responsive materials from many different research groups all across the world, we now see that there are many different types of functions being developed. And that includes the practical functions, for example, motion, communication, capture and release, regulatory functions, and some very primitive types of analytical functions. And because these types of functions are developed based on stimuli-responsive materials, we can now call these functions the stimuli-responsive functions. The hope here is to combine the different types of stimuli-responsive functions into a complex system that one day may be considered intelligent. This is an artistic impression of what an intelligent material may look like. Here, we propose to incorporate the sensing elements and the way to obtain the power for driving the functions, and to incorporate the analytical functions and practical functions. And these functions may include all the different types of stimuli-responsive functions developed by different research groups from all around the world. And by combining all these functions, we may one day be able to incorporate intelligence into materials. This approach is interdisciplinary. It depends on not just chemistry, physics, material science, but more importantly, it also relies on engineering and design. In the following slides, I'm going to talk about two examples for how we can incorporate intelligence into materials. The first example is to use very simple materials and to establish the relationship of these materials to advanced mathematical functions. In this case, we are going to look at the advanced mathematical functions of the derivative. The illustration here is as such. The importance of the derivative controller is because most stimuli-responsive materials only respond proportionally to the detected signal. And in this case, for example, we expect the time when the material starts to detect a signal, even though the rate of change of the signal is very big, it does not respond at all until when the difference is very big. But when there's a very big difference, it may already exceed some kind of undesirable threshold that makes the situation undesirable. And therefore, there is a need to analyze the derivative. Whenever there is a large rate of change of the detected signal, the controller or the material may then be able to respond immediately and therefore be able to bring down the undesirable detected signal to the desirable level. This type of operation may be useful for a lot of different types of applications, including for the case of controlling the release for the field of drug delivery. The question here is, how can we design a simple material that can analyze the derivative of the surrounding environment? Here we have a slab of stimulus-responsive hydrogel, and we coat one side of this hydrogel with the impermeable elastomeric layer. And because one side is impermeable, only one other side of this hydrogel receives the signal and contracts. And because only one side contracts, the hydrogel bends in this particular manner. And the rate of bending then is the way to sense the derivative. So this material here is an asymmetric material. It's not a bilayer. And the reason is because we have used a very flexible elastomer. And because of this very flexible elastomer, the mechanical property only depends on the hydrogel and not on the elastomer. And because of this highly adaptive material, we found that it is capable of doing the analysis of the derivative. Here from our experimental results, we see that whenever we have a faster rate of change of pH with respect to time introduced into the surrounding medium, we see that the hydrogel will bend at a faster rate than if the rate of change is slower. And because the material senses only the temporal derivative, it is not dependent on the absolute magnitude of the pH. Here we show that whenever the amount of pH is constant with respect to time, regardless of what the pH is, it can be pH 2 to pH 12, the hydrogel is always in a flat state. It doesn't bend. So from these experimental results, we can conclude that the simple piece of material does sense the temporal derivative and not the absolute value of the pH. We have performed some numerical analysis and theory, and what we found is that there is a mathematical relationship between the rate of bending and the temporal derivative. Here we found that the rate of bending scales with the square root of the temporal derivative. Not just that it can sense the temporal derivative, we can also use it for controlled release of drug molecules. For example, here, whenever we have this material, we can lay it on top of a chemical reservoir or a reservoir that contains drug molecules. And because the material controls based on the temporal derivative, this controller or this control release can also be used for analyzing the surrounding temporal derivative. Here we show experimentally that whenever the pH is constant, regardless whether it is pH 10 or pH 12, we see that there is no release of the chemical from the reservoir with respect to time. But whenever there is a change in pH, for example, from pH 7 to pH 11, there's release of the chemical from the chemical reservoir. These different lines indicate different rates of change of the pH from 7 to 11. And what we found is that the faster the rate of change of the pH, the faster the release of the chemical from the reservoir. We also demonstrated the experiments using a different range of pH, and we found a very similar set of results. So in conclusion, we have shown that controlled release can be performed based on analyzing the temporal derivative and not the absolute magnitude of the pH. If we now include not just any chemical within the chemical reservoir, but now we allow it to contain acidic solution, then we'll be able to build a full controller of pH that is based on analyzing the temporal derivative. In this case, if we use a disturbance of a basic solution, it will be able to allow the hydrogel to open and then be able to release acid into the surrounding environment and therefore be able to control the pH. Here we see that from experiments, we will be able to control the pH at the desired pH value that we want. So in short, we have fabricated a full controller in a particle that includes the sensing element, the computational ability, actuation, and release. And what we found from literature is that calculus, or specifically the derivative, has always been performed using a computer. So this is the first demonstration that calculus can be performed without the use of a computer. In my next example, I will show that how we can construct logic gates via design of the stimulus-responsive hydrogels. Here in this case, we have two stimulus-responsive hydrogels. The first is the pH-responsive hydrogel. The second is a temperature-responsive hydrogel. We stack them close to each other, and then we have a piece of flexible elastomer. And then we also have the outlet channel that links to a chemical reservoir. So what we can see here is that we can construct the OR gate. For example, if both the hydrogels are now in their contracted states, we can see that they do not push out the flexible elastomer, and therefore it allows the outlet channel to be open and for releasing the drug molecules. But if one of the hydrogels expands, the expanded hydrogel will now push out the flexible elastomer and therefore blocking the outlet of the channel and preventing the release of drug molecules. Because it only requires one of the hydrogels to expand, here we can establish the OR logic gate. And via design, we can also construct the AND gate. For example, here, if we just include a little gap in between the two hydrogels, we will need the two hydrogels to expand. In order for the hydrogels to expand into the gap between the hydrogels and also to push out the flexible elastomer. And in this case, because we need both hydrogels to expand, we have fabricated the AND gate. And based on the same kind of approach of design, if we have the different placement of the hydrogels and the different design of the valve controlling the outlet of the channel, we are able to fabricate different types of logic gates, including the NAND gate, the NOR gate. And in this case, we can also fabricate integrated circuits that involves the combination of different logic gates. And in this case, we have demonstrated the combination of the AND and OR gates. We have also demonstrated the case of the AND and NOR gates. And not just the construction of the integrated logic gates, we show that we can also use the logic gates for controlled release by combining the logic gates together with a reservoir of chemicals. And here again, we see that the release of the chemical depend on the logical sequence, for example, for the case of OR gate and for the integrated circuit of AND plus the OR gates. Because we have shown that the integrated circuits can be used for controlled release, we believe that we will be able to fabricate smart particles that include massive number of these logic gates fabricated on the surface of this particle for performing high-level analytical functions of the surrounding environment. So in conclusion, we have seen that we can incorporate analytical functions into materials, and we have shown two approaches. The first is to use just simple materials and establish direct relationship between the materials and advanced mathematical functions, for example, calculus. We have also shown that we can construct integrated circuits from just the design of the stimulus-responsive hydrogels. Here we have illustrated that high-level analytical abilities can be achieved via this interdisciplinary approach that involves material science, chemistry, physics, and importantly, engineering and design. So the last conclusion here is that we now have the ability to combine complex analytical functions and practical functions that allow us to construct truly self-powered, autonomous, intelligent materials. This is the end of the presentation. Thank you very much.
Thank you very much, Xiaoling. I see you're with us now. That was, again, beautiful science, and thank you once again for being on time. If I may ask a quick question, since we have a second, how far can one push the calculus? Can one imagine being able to be responsive to the second derivative, for example?
That is not something that is immediately obvious to us, at least. I think there is a possibility that we can extend the concepts a little bit, but I have to say that is not immediately obvious. It sounds challenging.
Well, really interesting work. Thank you very much for sharing it.
Thank you.
Okay, so our next talk is going to be Stefan Sieger from the University of Zurich, talking about super anti-wetting polymeric nanocomposite materials from coating to bulk material. Stefan, maybe you can go ahead and just share your screen, and then we'll wait just a little bit.
So you see my screen?
See your screen. Perfect.
Okay, good. Then I'm ready to start.
Let's go.
Okay, perfect. So at first, thank you very much for the invitation to give a presentation here, and thank you all the people listening now. I would like to talk about super anti-wetting materials, and maybe some of you remember that I have spoken at the same occasion, I think it was 2 years ago, about super anti-wetting, and this means mostly water repelling coatings. And I presented a work. This is we started this work many years ago, and now finally we have some products even in the market. This is a kind of coating based on silicone nanofilament technology. And the principle of superhydrophobicity, of course, is that not only the, let's say, hydrophobic nature of the material is sufficient to achieve superhydrophobicity, but you also need this very rough nano or micro topography. And this is shown here. You see this silicone filaments we grow look exactly like this, and this is a principle here. So this hydrophobic nanostructure leads to a super hydrophobic surface. This is a water droplet with some ink to make it better visible on such a surface. The chemistry is very simple. It's just polysiloxane chemistry, and of course the whole material is also very cheap and an inexpensive process. So this is the surface coating, and just a brief remark, because of course the question arises how we can make a one-dimensional growth of silicone. Usually if you do this polymerization reaction, you have a bulk polymer. And I just want to mention this publication. You can look in detail if you are interested. But what we do is, that we use basically a small water droplet, a nano droplet on a surface as a reaction confinement. And this water droplet absorbs the ingredients necessary for the reaction from the gas phase. And then if everything comes together in this droplet, the polymerization process starts. The polymer is deposited on the surface, and on top is still the water droplet executing all this reaction all the time, and then we get a one-dimensional growth in the diameter of the structures are basically the diameter of the droplet. Okay, so far to the coating, but now everybody knows that coatings are vulnerable. Yeah, so you have if you scratch over a surface, then you get a scratch, and this means also super hydrophobic surface get leaks, and then water wets with the time more and more the surface. And we thought about how we can overcome this problem. It's not always a problem, but for many applications it is. And so we thought, can we make a super hydrophobic bulk material And so, in other words, if you scratch over the surface, you generate a new superhydrophobic surface. So, as result is that you cannot destroy the superhydrophobic property. And the pathway we went was is shown here in this part of the picture. What we did is we used a silane or two components of silanes, mixed them together. So this is now a polysiloxane, a hydrophobic structure, but of course it is not. It does not show this nanotopography we need, this roughness. And so what we did, we mixed polypropylene particles with this PDMS here together. So we have a composite material, and the idea was that we generate then a topography which is sufficient to increase the hydrophobicity beyond a little bit artificial value of contact angle so that we can say it is super hydrophobic. And at the same time, we also thought, okay, if we have the super hydrophobicity, it would also be nice to have self-cleaning properties. The self-cleaning properties are sometimes generated by superhydrophobicity itself. This means a rolling droplet takes dirt from the surface, and then we have this a kind of self-cleaning, but here we wanted to increase this effect by a photocatalytic process. And so we added as a further ingredient this dicyandiamide, forming this carbonitride here, which is known to convert visible light to chemical reactivity, and then impurities should be decomposed. Okay, so this is a principle. And what I just want to show on this picture is here, this is a material we generated. So it looks, of course, like a bulk material, but of course you cannot see any special properties here. But if we look a little bit deeper, the scanning electron microscope images you can see here, this displays in a nice way that we really get this topography, this roughness in the it is not very much in the nano range, but it is in the micron, sub-micron range on this border roughly. So in so far we can generate this topography by this strategy. This is a good thing. And then we did the EDX experiments as well to look if we find all the elements we have put into the mixture. Of course we do, they do not disappear. And then I think the most important picture is shown here on the bottom left. Here we have a water jet approaching this bulk material, the surface of this bulk material, and you see the repellents very nicely. So we have really a very hydrophobic material. Okay, this can also be seen here, a water droplet approaching this surface, and it's bounced off completely in a very short time without leaving some visible water residues on the surface. So we have a water repellent surface, that's clear. Okay, the water repellence is usually measured, or one very important size or is a value is a contact angle, and what we see here, we find a contact angle of 170 degrees, and I just was talking about this a little bit artificial level or border between hydrophobic and superhydrophobic. This is usually, it's generally accepted that it is 150 degree in contact angle. So we are far beyond this. So certainly we have a superhydrophobic surface on the, at least the surface. Coming to the bulks in a second. Another value is the sliding angle. This means how much you have to shift the surface that the water droplet rolls off, and this is below 10 degrees, also very good. So we have certainly a very nice material here generated. Okay, then what we have done, of course, is now, and this is a very important thing, to see if we have really a bulk material which shows the superhydrophobicity. And here we have done just some abrasion experiments, moving a rough surface forward and backward with 530 gram load. So this is a lot, and moving forward and backward, and then removing the surface layer on the material, and a new material comes up then on the surface. That's clear, and we do these abrasion cycles 150 times forward and backward, and you see that the contact angle and also the sliding angle do not change at all. This means what we expect is true. We have a superhydrophobic bulk material, and the superhydrophobicity cannot be destroyed by scratching the surface or destroying the surface or ablation of the surface. Okay, we went also deeper, cutting the material in several pieces and slides. This is shown here. You also see that we have still the two levels here. Even if you go to 8 millimeter in the material, so you see it's really working, the idea. And here we see a broken bulk material here. This polymer and a droplet shows also this repellence, and the same is true with water droplets falling down on the surface and bouncing off. Good. Now, what is very important for bulk materials, of course, is the mechanical stability, the mechanical properties. And here we measured the flexural strain, tensile strain, and compressive strain. All three show good values. I mean, it's not world record, but this is, of course, not the goal of the project. We have a good project, a good material, good stability, including the superhydrophobicity. Okay, we also checked the chemical resistance of the material, and I mean, when I say materials, and I also mean, of course, I mean the superhydrophobic property. And we have checked it against HCl, against sodium hydroxide, and organic solvents, and you see that it is very stable against all these very aggressive liquids here. Good. Now, finally, I come back to the self-cleaning, the photocatalysis, the inherent photocatalysis of this material. This is also very interesting to see. Here we measure again the contact angle, and this is in a way the virgin material here. We have this 170-degree contact angle. Then we apply some impurity. Impurity in this case is oleic acid. The surface is contaminated, and then we irradiate it with light. And you see, at first we contaminate it, then you see how the contact angle drops down to a value of roughly 110 degrees. This means the superhydrophobicity is disappears. It's just hydrophobic, but not superhydrophobic anymore. Then we irradiate it, and then it climbs up again to 170 degrees, and this can be done several times, several cycles. And we have this very nice self-cleaning effect, obviously. More chemical analytical approach is to look on the infrared signal of this oleic acid before and after catalysis, and you see that this peak is disappearing. This is what we expect. And here is a macroscopic experiment, contaminated water rinsing, and after photocatalysis, it is clean again without any impurities. Okay, this is what I have to say. In summary, we have a very simple method to fabricate this superhydrophobic bulk material, which is, by the way, fluorine-free. This is not so usual. but it is good for in terms of sustainability. Yeah, we have very stable superhydrophobicity, as I explained. Mechanical stability is good, and we have the self-cleaning effect included in a way. Okay, this is what I want to say. I have to thank my university, of course, for the financial support and European Union support. And I have to thank all the co-authors and other people involved in this project. Thank you very much.
Thank you very much, Stefan. That was also some really beautiful work. And again, everybody's established a strong track record of being on time, putting pressure on other speakers to do the same. Quick question about the long-term stability of your photocatalytic component. I mean, is that expected to last years? Is that a weak link that needs to be worked on? If you could just comment on that.
Yeah, I mean, it is too new to say really. We do not have reliable results about this, but it looks very good at the moment, and we certainly will see how long it lasts. And yeah, it's difficult to say how the long-term stability in terms of, let's say, 20 years or 100 years or so is. I cannot answer this today, but the properties look very nice.
Really nice work, Stefan. Thank you very much. So our next talk is by Harn Wei, which would be, I believe, a recorded video. He is from the Indian Institute of Science, and the talk is titled Effects of Silica-Rich Biochar on Cement Mortar Hydration Kinetics and Durability Under Chloride and Sulfate Environment. If you could load up the video, thank you very much.
Very good morning to all of you. My name is Han Wei Kwa, and it's a pleasure of mine to be able to share with you our latest work on the effects of silica-rich biochar on cement mortar. This is the outline for my talk this morning. And I will begin by saying something about biochar. Well, biochar is a solid material obtained from thermal decomposition of organic matter, such as biomass in the form of wood and leaves, under an environment which is limited in terms of the supply of oxygen and air. As you can see here from the diagram right below here, the key products of pyrolysis can be in the form of synthetic gas and bio-oil. And of course, there's this solid byproduct called biochar, which can also be used for a wide range of purposes, including to be used as soil enhancement, and in our case, as an additive or even cement replacement in concrete. The outward appearance of biochar is very similar to the more widely known charcoal. But of course, to make biochar, we have to be very selective with the feedstock as well as the production conditions. The field of biochar concrete research is a pretty young one. In fact, the first paper, substantial research article on it, was only published about 9 years ago by a group in South Korea. And right after that, we have a series of work that stretches for about 4 years that look primarily at the different mechanical strength aspect of concrete and mortar, and examine how biochar serve to enhance these different properties. I first got to know about biochar concrete only back in about 2014, 2015. And the key motivation for me to look into that is to look for a solution for a rather challenging problem in Singapore. And that is that about 60% of building-related complaints and problems that we are facing now in Singapore has to do with the transport of water in concrete. So not too long ago, we published an article in the journal known as Cement and Concrete Composites, in which we look at how different kinds of biochar can help to increase the water tightness of mortar. And these are the key results. In a nutshell, what we found is that when we have biochar, and in this case, a special kind of biochar that is unsaturated, we're able to dramatically reduce the depth of water penetration. And concurrently, we also find that this particular combination of sample of biochar containing mortar happen to also have the highest 7-day and 28-day strength. So in summary, what we found is that indeed, when added into mortar, biochar can help to reduce the water penetration by about 57%, and that's quite a lot, and at the same time increases the compressive strength by 16%. So that forms the basis, the foundation of the work that we did later on. And extensive examination using FCM images also show us that the inner wall of biochar pores, that means these are the pores on the biochar, also provide the additional surface for formation of cement hydration products. So to the extent that right now we know of 4 or at least 4 different reasons why biochar works. The first is that the sheer size of the biochar enables it to densify the cement matrix by acting as a microfiller. And secondly, the very fact that it has different kinds of pores on the surface allows it to densify the region around it simply by taking in the water, and this will also reduce evaporation from the region around it. And as I mentioned just now, after the water has been, the free water in the matrix has been absorbed into the pores, the surface of the pores begin to act as nucleation sites for the formation of cement hydration products, and therefore driving and sustaining hydration. Last and not least, but not the least, some of the water contained in a biochar is known to also diffuse out into the surrounding in order to sustain cement hydration in the regions. And this is especially true when water is lost in this region, either via bleeding or evaporation. So the big question, therefore, is whether we can make use of these properties of biochar in enhancing water tightness to also solve the problem, to address the requirement for us to have more resilient buildings and infrastructure in a climate which is changing, and of course in the future when we have to face the rising sea levels. So with this in mind, we came out with the aim to investigate the effect of 2 different kinds of biochar. One that is produced from rice husk and the other one from mixed wood waste, to see how it may enhance the different properties of cementitious mortar when it is exposed to 5% sodium chloride and 5% sodium sulfate solutions. Right, these are all done with a big number of 50 millimeter cubes cured in water, chloride, or the sulfate solution for 120 days. So over here, you get to see our composition mix. From here, you can see that the control or the cement contents of control is gradually decreased as we put in an equivalent amount measured in mass, in terms of mass, of biochar into the mixture. What we find interesting is that the more biochar we add in, the higher the surface dry density, okay, which is actually telling us that the pores on the biochar really contribute to the densification of the matrix as a result of absorption and temporary storage of the free water in a matrix. So here are the key results. We find that upon comparing the elemental composition of these two different kinds of biochar, not surprisingly, I would say that the carbon contents of a mixed wood biochar is a lot higher. And of course, we are pretty glad to also see that in the case of biochar from rice husk, the silicon level is high as well, which is pushing about 20%. What is even more important is to find out the percentage of presence of silica. And in the case of biochar made from rice husk, it is about 16%, very close to what we are seeing in cement particles. All right. In that case, it is about 20%. And when we measure the heat release from the cement hydration process, we found something really interesting. While the rest of the curves are pretty much the same, we find that by adding 2% by weights of biochar made from rice husk, right, there is a slight delay of the building up of the heat of hydration, and that can be attributed to the temporary covering of the surfaces of the CaSH, which is the calcium aluminosilicate hydrate, all right, on the surface of tricalcium aluminate, right? And this is only temporary because it's only a matter of time that the layer of CaSH is removed, and therefore allowing the water to come into contact with the tricalcium aluminate underneath. And what's more, we find that after exposing our samples to sodium chloride, right, there is a very clear advantage of having 2% biochar made from mixed waste wood in the mixture. And in fact, over here, you'll find that by putting 1% is even better. Right. Other than comparing the compressive strength, we also compare the change in the strength compared to water curing. Okay, what I mean by that is that, for example, I compared the strength of mortar containing biochar from wood added at 1%, cured in sodium chloride, right, to the strength of the same kind of sample but cured in water. And of course, after 120 days, okay, most of them perform worse off than their counterparts cured in water. But what is more interesting is that you can see the pattern here, and that is that when I have only 1% presence of any kind of biochar in mortar, the reduction in the strength compared to their counterpart cured in water, right, is not as much. The drop is not as much as if I were to add 2%. So in other words, what I found is that mixed wood biochar added at 1% by weight strengthens mortar even after being exposed to sodium chloride solution. And it also records the lowest strength reduction over 120 days. And a similar conclusion can also be drawn when I expose these samples to sodium sulfate solution. So what may have happened? So this is a mental picture that we had on what might have happened. And basically, whenever we have biochar, right, in the mixture, it helps to absorb water into its interior. And as a result of that, help to recede the waterfront. So you can imagine that the waterfront, all right, signified the line as indicated here, when water, in this case, fluid containing sodium chloride flows from the right-hand side towards the left-hand side. So with biochar around, a thick wall made up of ettringite and the Friedel salts helps to impede further ingress of salt, and therefore limiting structural damage due to any expansion and therefore crack formation as a result of accumulation of ettringite. In fact, all these can be seen from some of the SEM images that we have took. And we have also found evidence that the 4 factors, how biochar strengthen the concrete and reduce the permeability, can be also found in our SEM images. For example, this picture over here shows how a biochar can help fill a pore, all right, in the cementitious matrix. And of course, as time goes by, the accumulation of ettringite and FS, right, cause further cracking and therefore reduction in strength in all of our samples. And this is shown by this hairline crack over here. The higher the percentage of biochar, right, we find that the higher the tendency of some of the pores in the biochar being only partially filled. And this actually lead to higher porosity, which translate into lower strength as well. And especially for the case of biochar from rice husk and added at 2%, right, we find that the chemical reaction between the sulfate salts, right, and the silica, which is present in RHB or the biochar made from rice husk, they will serve to weaken the bonds on the surface of biochar and therefore accelerate the debonding of the biochar from the surrounding matrix, which leads to lower strength as well. In conclusion, what we found is that just by adding 1 to 2% by weights of biochar made from wood has the potential of increasing the compressive strength of mortar by 8 to 11%. All right, and at the same time, reduces the total salt absorption after 120 days, okay, substantially. And of course, the exposure to a sulfate solution leads to an increase in strength at 42 days. This is not something surprising, and at least in our test, right, we managed to get a result which is in agreement with some of the results from the literature as well. And finally, after 103 days of exposure, all right, we found that by adding 1 to 2% of the different kinds of biochar studied here, we have the potential of getting an increase in compressive strength of between 14 to 17%. So we would like to thank the Ministry of Education from Singapore for providing the fund for this research. And as a parting remark, I would like to bring your attention to one of the new journals.
Gee, unfortunately, I think we have to stop it because we're now over time. Thank you very much. And thank you to Hornway for that talk. Our next talk is by Mohsen Badshah from the University of California, Irvine, talking about dynamic materials inspired by cephalopods. Whenever you're ready, go ahead and share your screen and let's go.
Thank you so much, Chair. I'm Mohsen Badshah from University of California in Irvine. Today, I'm going to talk about the dynamic material inspired by the cephalopods. Here is the just give, like, it's not allowing me to have. I don't see.
What about that bottom icon next to the zoom? Will that let you maximize?
Yeah, I just, like, it's not allowing me to move. Okay. Sorry about that delay. Sorry about that delay. Yeah. Today I'm going to talk about the dynamic material inspired by the cephalopod. Here is the outline. Like, I will talk about thermal management technologies for personal comfort, then move forward towards the design, of the thermoregulatory material inspired by the space blanket and the cephalopods. And later I will talk about the fabrication and optimization and I will conclude. So coming towards the major problem, like in the world, like we are consuming like the energy of like 160,000 terawatt per hour globally. And from that, only 14%, which is like 30,000 terawatt, is only used in the United States. And from that 30,000 watt, 40% of the energy is consumed by the building, from which the 36% is just used for the heat and ventilation or the cooling system for the personal or the thermal comfort of the people or the living in those buildings or working in those buildings. So coming towards like the major issue, in order to decrease those energy consumption, the thermal comfort is really important, or the changing the temperature range into some extent to decrease the energy consumption is really important. Now, like what is thermal comfort? It's basically like where the human or the person feel comfortable. Like in case of like females, they have like a comfortable temperature higher than the males, and this comfortable temperature basically decrease down with the sensation of the age or increasing age. And mostly people feel when it goes for the like higher temperature. So that's why there is a need of the systems or the clothes that require to localize the thermal management to feel the people or the humans comfortable. To make the human comfortable, there are different systems like passive and active systems, mostly utilized like passive technology is matured, inexpensive, and require no input energy, but it's static and have limited control in the hand of user. But while the dynamic control is mostly expensive and required a high input of energy. So we need a technology that's ideal, which have the pros of like passive and the active system. With that regard, like we are moving forward with the concept of the space blanket that have the potential to reflect the thermal radiation. And that's basically one kind of example that is basically mostly used in outside of like picnics or some passing through, and the rains. There are some examples mostly used into the space blanket area too. Here is like inspiring from that space blanket. Columbia Omni Heat basically develop a material that can reflect the heat or the infrared and leave the body like heat inside the body. So basically, it's showing like how the light is moving out from the surface of that Columbia heat jacket. And while moving forward the solution, like we inspired from the cephalopods that have the ability to basically change the colors based on the electrical pulse that's generated within the body of the cephalopods. Like you can see that one cephalopod which is hiding, and when some like danger comes, it change the colors and move away with the like its perception. So here, like what happened in cephalopod is kind of chromatophores and electrophores, which have some electrical pulse connections. Like an example, you can see. So these are the electrophores which basically create the electrical pulse connection, which reflect the basically light based on the requirement. So inspiring from like space blanket and the cephalopods, we design a material that works as like give the ability of the passive and the active system while radiating or the blocking the heat or the infrared from its material. And our group published that material, that research in 2019 in Nature Com. While proceeding further for this research, we need further optimization, like what's the best condition to have the best performances of these kind of materials. So moving forward, like here is a complete fabrication method. Like we have initially a support substrate that's basically silicon wafer on which we are fabricating some nanostructure. I will talk about how we are fabricating, and in that next step, we are embedding those thin film nanostructure into the polymer and finally delaminating from the surface of the silicon wafer. So while moving forward, the selection of material and selection of the fabrication technique is really important. So we selected the copper as like an infrared reflecting layer, which 100% reflect the infrared light, and choose the material as a copolymer SCBS, which have the open band into the infrared. So it's not blocking any kind of infrared while it's passing through. To fabricate the thin film or thin film structure, we choose the glancing angle deposition technique, which allow us to fabricate like various shape of the structure, like vertical, slanted, zigzag, or spiral-like structure. That we fabricated. I'm not going to talk because that will take more time how we selected, but we selected the slanted angle structure and apply the planar layer in between as a support layer and optimize like how that affects. And that affects directly basically the cracks or the opening within like that, allowing the infrared to move forward and find like the 20 nanometer planar layer with the 90 nanometer slanted structure helps to make a uniform structure that helps us to achieve like the best performance in terms of infrared transfer. Like initially at 0%, it's 100% blocking, while when it's open up, it allow the light to move forward. That's why our transmittance increase like up to the 40%. And that's basically that like with at the 100% strain while we are applying. So now coming back towards the like thermal temperature, that there is a like set temperature, set point temperature, which basically allow any kind of human or to maintain its temperature while maintaining the heat skin. So people into the cold environment sometimes feel cold, warm when it's gone. So there is a requirement of this kind of material. And when we tested the various material, like it's like space blanket is giving us like the temperature range is 13, while the rayon textile material is giving us the temperature like it's the blanket basically working in both kind of like these for various seasons, like starting from summer to the winter. But in our material, if we use a single material, it works as like a space blanket at 0% strain, but works as a similar like a rayon textile material when it stretches at the 100% strain. So to confirm its functionality, we did a control experiment using like space blanket and in our composite, like you can see in the picture, that the infrared camera images are there. We basically set up an experiment where one hand have no material and other hand have the material and compare its performances while moving forward, like wearing the sleeves, and got like the control like with the application of the removal of that composite, it changes the temperature up to the 1 degree change. That's allowing us to move further for further investigation. So that's so far. And in the end, like I would like to conclude, like our material which we fabricated is fabricated through the like low cost nanofabrication process and over the area of 160 centimeter square. And we fabricated that material that can modulate the heat, basically the infrared up to the like 40% of it with a switching ratio of like 2, and have the potential to set the range of the 8 degree, which correspond to the decrease of the 30% energy consumption into the building. So that allow us. In the end, I would like to acknowledge and thank to my group and my supervisor, especially and the funding agencies like the DARPA and ARPA-E for supporting this whole research. And I'm open towards the like, I will appreciate your questions if you have any.
Thank you very much, Mohsen, for that interesting talk. Trying to see if there's any questions in the chat. If anybody has a question, please feel free to type it in the chat and I will read it off. Mohsen, can you say anything about the mechanical stability with time as you apply and take away the strain? Do you think there will be any cracking that's induced with time, or is it pretty robust?
It's a pretty robust. Like we did analyze the performances up to the 10,000 cycle by running it, and then tested like the infrared performances, which pretty much like overlapping the 0% performance. So although that in the initial it's like pretty much flat layer, but with the cycles, it becomes like a crack, which you saw onto my initial FCM images. And these cracks remain pretty much similar across the cycles of those 10,000 cycles. And that's why this performance after the 10,000 cycle is pretty much similar, like the one we had here. So we had those testing in our.
Great. Thank you very much. Really interesting work. We were meant to have a talk from Ivo Stachev from the Institute of Physics from the Czech Republic. The talk was going to be titled High Frequency Operating Shape Changing Resonators Utilizing Unique Properties of SMA Elements for Microrobotics. Unfortunately, we do not, I believe, have a recording. And so we will have to take a break until 11:50 when we will have Konrad Schwanitz present. And so I will see you all at 11:50. Hi, Conrad. You could share your screen and then we'll get going in 1 minute.
Can you see my screen?
I can see it. Thank you.
Okay, perfect.
Okay, our next speaker is Konrad Schwanitz from Vika. I hope I'm pronouncing that right.
Yes, it's very simple.
Okay.
Yep.
And the talk title is right there, Self-Adjusting Boron Nitride Mask for Reactive Ion Etching. Conrad, thank you, and please get going.
Thank you for this nice introduction. So the topic is very simple, and hopefully it's not too simple for you guys. So it's about the self-adjusting boron nitride mask as it's shown here from the bottom side up. So it's a very simple problem we have. It's just about etching free with a selective reactive ion etch process. Let me allow just one slide advertisement about the company Vika. So we have a product range from pressure, temperature, level, force flow and calibration technology to SF6 technology and tailored engineering solutions. We are globally present in over 44 countries, and we have a lot of production, 50 million units worldwide. And our measuring ranges from very low millibar, 0.5 millibar, up to 15,000 bar, which is sometimes used in chemical reactions and synthesis in big, really process plants. And the temperature sustainability ranges from some products from minus 250 Celsius degrees up to 1,800. So far, Vika maybe is not well known by its name, but if you work in the laboratory, and I'm sure you have seen this manometers, and most of them they're from Vika. These are the classical devices, but we have also electronic measurement parts, pressure measurement parts shown here and here with different materials. And we have also level measurement for big tanks and so on, and calibration technology. Okay, now we go into the matter. This is the thin film pressure sensor shown here in the cross section. So we have stainless steel body, a bulk material, which is drilled to a very thin membrane. And due to pressure application, the membrane bends. On top of the polished surface of the sensor, we have an insulation layer comprising of silicon dioxide. And on top of that, we have a metallization structure applied by lithography processes. It's mainly nickel chromium, and that works as a piezo-resistive element. So due to pressure application, we have some stress and some strain, and then this is arranged in whetstone bridge, and then it changes its resistivity, and we can measure an electrical or converts the movement of the membrane into an electrical signal, which we can withdraw and read out. On top of this, this is a part of the problem which I would like to talk about. We have some nickel bonding pads, and they are covered entirely by a passivation layer in order to make the sensors sustainable against environmental influences, mostly like moisture. In order to etch this selectively free, we did some tests with different materials I would like to talk about in the following. But shortly, I would like to introduce the reactive ion etch process. The tool is shown here. We use this module here at the left side. Here's a very simple schematic of the reactor, of the chamber. It's an inductively coupled reactor, which has outside copper coils in order to induce or to ignite the plasma, to induce an electrical field to ignite the plasma. The gas inlet is from top, and we use CF4 and argon So it's a reactive ion etch. So basically chemical etch, but with a physical component by these argon ions. They are accelerated towards the surface of the sensor or the assembly, shown here in red, by modulation of low frequency. So we have a bias. And here we have the process in very simple pictures. So we have the fully passivated sensor surface. We put here the reusable hard shell shadow mask on top of it. Then we apply the plasma, and we have the etched free bond pads. So the problem is very simple, but the devil is in the detail, so to say. We need a really residual free surface in order to apply in a subsequent process wire bonding. And this is a big problem, or used to be a big problem, while we are using alumina as a mask material, because alumina shows here after several times, about 50 times usage, some optical peculiarities which indicates that something is going on here on the surface. And also we had some problems on the sensor surface. Whereas with boron nitride, which is now our solution, the hard shell shadow mask looks rather unimpressed by the process. These dark spots come from the geometry of the adapter underneath. They are drilled holes, and you change the plasma conditions. That's why you have some redeposition effects here. In order to explain how we apply the mask, you see the picture down here. This is a mask from underneath, and we put it here on the assembly. It's a carrier comprising of 120 sensors. We just flip it on top, and it could be very precise depending on the mechanical tolerances of the mask and on the carrier. Looking into detail on the sensor surface, in the case of the alumina mask used, we see in the bond pad region, shown here, some dark areas which are residuals when we try to we investigated it by scanning electron microscope. We see some fine particles about 200 nanometer in size scattered all over the surface. On this surface, wire bonding is impossible almost. It's not feasible. Whereas when we apply the boron nitride, we have a rather pristine surface with respect to optical experience. We try to resolve it also with EDX spectrometry. And here in the red spectrum shows the case where we use the aluminum mask. It's on the nickel bond pad. We see some fluorine and aluminum peak. So we suggest, we have some aluminum trifluoride particles on top, whereas using the boron nitride mask, the fluorine and the aluminum peak is absent. So we have rather, for our at least purposes, rather pristine surface, which is fully bondable in order to contact it electrically. Looking further into detail, in order to explain how the contamination is stacked on the surface, we did a line scan over the bond pad region. Here you see the bond pads, the white or the light gray areas, and in between the dark gray area is the insulation from underneath. And looking at in the profile, we see, interestingly, on the nickel bond pad, we have a higher concentration of carbon, shown here in the green line, and we have a higher concentration on fluorine and aluminum. So that means the aluminum trifluoride we already have seen, but we have also some byproducts by the reactive ion etch process, the carbon fluorides polymers. And when we just, how to say, we withdraw the carpet underneath of the residuals, like if we etch away the underground, like here in the region in between, the residual has no opportunity to settle down. That's why it's the contamination here is much lower. But this is not really the way we wanted to go. The boron nitride mask didn't show such peculiarities on the nickel bond pad surface, but the mask itself has shown some strange behavior, so to say. A new mask is rather smooth. We investigated it with optical profilometry, and if we used it for 50 times, we have a rough surface. Unfortunately, the thickness of the mask is not etched away layer by layer, so we don't have a precise measure in the industrial process in order to say, okay, the mask is thin enough, we can exchange it. We need to measure the roughness. And you can see it here in the roughness values as well, that we have an increase in roughness over time. Furthermore, we investigated it also with EDX, the used side and the smooth unused side here shown here. In the backscattered electron mode, you see the lighter side on the left, which implies more, which indicates more heavier elements, whereas the darker side, we have lighter elements. And I forgot to say that we have a composite material. The boron nitride is not pure boron nitride, it's boron nitride with 1/3 comprising of silicon dioxide as a binder and stabilizer. And you can see it here in the results. On the unused side, we have more the boron in the nitride phase. And on the used side, we have more the silicon and the oxide phase. This is due to a different or a faster etch rate for boron nitride compared to silicon dioxide, as it is reported here in literature. The interpretation of the result is really simple. So this is our normal process. We have the formation of radicals and the etching of the silicon nitride by fluoride. And here is just a simple explanation why we have the residuals with the aluminum oxide mask, because in the periodic system of elements, lots of elements form solid state fluorides, like aluminum fluoride. There are only few elements like boron, silicon, carbon, tungsten and uranium, but uranium we couldn't get the mask, unfortunately. No, just kidding. The boron mask is very nice because we can cut it in 3 dimensions and we can apply it, and we just produce gases. And this is a key element for a residual free surface. I would like to thank my thin film engineering group at Biochar, my colleagues, and also I would like to thank the company Hense for providing the boron nitride mask, and the ACO, Institute for Analytical Services. I would like to thank the organizing committee to invite me to the talk. And last but not least, I would like to thank you for your attention.
Thank you very much, Conrad. Really interesting chemistry. We have a second for a question. I was curious, what happens as you start varying the fraction of the binder? I'm guessing you found some sweet spot, but what if you put in less or more binder? What do you find as far as degradation?
I have to admit, since I'm not from the academic research, we didn't vary the binder composition or the fraction of the binder, but this is a very interesting point. And if I have the opportunity to do so, I would like to do, really, but I don't have any data on that. What we did, we applied a pure mask, a pure boron nitride mask, yeah, and we haven't. Yeah, with respect to composition, of course, nothing changes, but we haven't seen any beneficial effects on the surface. So we are more from the application side. We, how to say, if the process works, that's fine for us, but it's a very interesting question.
Yeah, makes sense. Thank you very much, Conrad, and thank you for being on time. I appreciate that.
Thank you.
So I think next we have a recorded presentation, but I hope I don't butcher this name. It's Hugues Girard from CEA in France, and the talk title is Fine Control of Detonation of Nanodiamond Surface Chemistry Towards Functional Materials. Thank you, Chief, for loading.
Hi, my name is Hugues Girard. I'm a researcher at the French Atomic Energy Commission, and in this talk I will show you how the surface chemistry of the detonation nanodiamonds control their behavior towards functional materials. First of all, I will remind you how to produce this, how are produced these particles. There is two main ways. The first one is the milling of synthetic or natural microcrystals. Then you're gonna have good crystalline particles with a diameter ranging from 10 nanometers to few micrometers, and faceted particles. But you're gonna have a very polydispersed particles, as you can see it in this TEM picture. On the other hand, you have a detonation synthesis, which is a bottom-up approach. In this synthesis, then you can have quasi-monodispersed and spherical particles, as you can see it on the TEM picture, with a very small diameter, between 2 and 8 nanometers usually. But these particles, if they are very small, they are very prone to aggregate themselves and form small clusters of tens of nanometers. What are the properties of these nanodiamonds, whatever the mode of production? First, you're going to keep some of the bulk properties of the bulk diamond, like the semiconductive behavior with the band gap of 5.5 EV. Of course, all the mechanical properties of diamond and the thermal conductivity associated to the diamond. For the core, you're going to keep the chemical inertia of the bulk materials, and also in the particles you can have some of the famous NV or SIV centers, which are fluorescent centers, well known now for biomedicine or into quantum technologies. And as for bulk materials, you can have access to doped particles, for instance with boron. Then you have the surface properties of these particles, which of course are of great interest. You have the carbon-based surface chemistry, very useful to make further grafting on it. The tunable surface charge, here you don't need to use any coating, just by crafting the good chemical moieties at the surface of your nanodiamond, then you can have negative or positive zeta potential. I will come on that later. And this nanocarbon has been shown as one of the more biocompatible nanocarbons compared to carbon nanotubes, carbon dots, and so on. Oh, let's have a look on the application of these nanodiamonds. In nanomedicine, you can combine the biocompatibility of this nanocarbon and its surface chemistry to get a very good carrier of proteins, drugs, nucleic acid, and so on. At the same time, you can also use the fluorescent properties of the NV center, which can be found in the core of these nanodiamonds, to also have a very good emitter and labeling. In quantum technologies, people are using the magnetic properties of the NV centers to get some very efficient sensors, nanometric sensors of temperature, for instance, and other kind of sensing. In composite material, of course, nanodiamonds are well used for the mechanical properties they can bring, and they can enhance into polymers. Lubricant as well for the wearing properties of the diamond. And more recently, people are also interested by the catalytic properties of the nanodiamond, either playing on their surface chemistry and promoting some sp2 carbon at their surface, which can be useful for some catalytic reactions, but also using the core of the diamond, which has been shown to be quite efficient to promote some charge, like solvated electrons or radicals, as we're going to see it later in this presentation. Now, where to find and how to find these nanodiamonds? Then there is dozens of manufacturers all around the world of milled or detonation nanodiamonds. But what is important to know is that each manufacturer will have his own purification process, which will give you different kind of what we call as received particles with more or less sp2 at the surface, more or less carboxyl groups or hydroxyl groups, and so on. So this is why it is very important to have some homogenization treatments in order to really control by yourself the surface chemistry of the particle you're going to use. Here I will show you how to control your surface by using oxidizing treatment. Let's say that there is two kinds of very efficient oxidizing treatment. The first one is air annealing. If you go up to 500 degrees with detonation nanodiamonds, or a little bit higher with milled particles, then you will be able to etch all the non-diamond phases like sp2 or amorphous carbon, and at the same time promote the formation of carboxylic groups at the surface. And from these carboxylic groups, then you can play with wet chemistry to make the reduction, and for instance have access to hydroxyl groups to make esterification and so on. So air annealing is one type of efficient oxidizing treatment. Another one is acid treatment using nitric and sulfuric acid. Then you can have quite the same kind of oxidized functionalities at the surface of your nanodiamonds. Another way to homogenize the surface chemistry of your nanodiamonds when you receive them is to perform reducing reaction. By reducing reaction, I mean either annealing into vacuum or argon inert atmosphere, which will promote the desorption of your oxidized groups from the surface if you reach at least 500 degrees, and the formation of some sp2 carbon at the surface. Then you're going to have what we call smoothly graphitized particles up to onion-like carbon if you go very high in temperature in this inert atmosphere. And with this sp2, sp3 carbon particles, then you can play a lot with the surface chemistry then after for instance catalytic reaction. Another way to reduce the surface of your nanodiamonds is to make hydrogenation. Hydrogenation either by annealing into H2 atmosphere or by using a plasma, microwave plasma for instance. Why trying to make hydrogenation of your nanodiamonds? Because on diamond, hydrogen is maybe the simplest way to obtain a homogeneous surface when you saturate all the carbon dangling bonds with hydrogen. This was first used for bulk diamond and now is quite often used onto detonation or milled nanodiamonds to get particles with a very good homogeneous surface chemistry to start with. How to make this hydrogenation? So as I said, by plasma or annealing. This here you have pictures of setup we have in the lab, either by microwave plasma if you need harsher condition, depending on the kind of particles you use. Typically we make the hydrogenation from 10 millibars up to at atmospheric pressure of hydrogen. Temperature, depending if you use plasma or annealing, goes from 500 degrees up to more than 800 degrees. Now if we focus on this hydrogenated nanodiamonds, let's have a look on the characterization. We work on this hydrogenation of nanodiamonds since more than 10 years now, and so all along the years we had access to different type of advanced characterization, from XPS showing how you can decrease the oxygen level at the surface of your nanodiamonds, FTIR in which you are able to see the CH formation at the surface of your nanodiamonds. At the same time you see the vanishing of the CO bonds from the surface. We also check, of course, by ICP-MS that our treatment, either by plasma or annealing, do not bring some impurities into our nanodiamonds. It was not the case, of course. We also play with tritium instead of hydrogen in order to make the labeling of our nanodiamonds with tritium, and to have a look in which part of the particles is the hydrogen or the tritium. And in this paper in 2014, we have seen that finally more than 10% of the hydrogen goes into the core of the particle. Dealing with hydrogenation of nanodiamond at high temperature, of course, we can have the risk to promote sp2 carbon at the surface of our nanodiamonds, and this is why we also characterize thoroughly our nanodiamonds hydrogenated ones with Raman, with HR yields as well, with NEXAF and with NMR, and they all have shown that the hydrogen really goes onto the sp3 carbon, and if there is sp2 at the surface, it remains at a very low concentration and just a few patches of sp2 aromatic molecules at the surface of our nanodiamond. A very good surprise when we started to work with this hydrogenated nanodiamonds was to see that finally, after the treatment, you can directly disperse them into water and have they behave a positive zeta potential natively. Then you can form a very stable suspension of your hydrogenated nanodiamonds in H2 in water. And this positive zeta potential is quite stable from pH 4 to pH 10. And we associated this stability and this behavior due to some very specific organization of the water molecule on this supposed hydrophobic surface of our hydrogenated nanodiamonds. Now that we have seen how to control the surface chemistry of nanodiamonds, let's focus on two hydrogenated nanodiamonds. First, toward nanomedical application, we used these hydrogenated nanodiamonds for their cationic behavior. In different papers, we use these nanodiamonds to deliver scRNA into cells, in vivo and in vitro, in order to treat the Ewing sarcoma tumor. And in this paper of 2020, I believe, we also use tritium labeled particles in order to follow them and to make some tissue distribution. Another way to use hydrogenated nanodiamonds is, let's say, an active way in which nanodiamonds are used as a radiosensitizing agent toward cancer treatment. Indeed, 10 years ago, we have seen that if you make the irradiation with gamma rays of cells in which you introduce hydrogenated nanodiamonds, then you're going to increase the amount of reactive oxygen species promoted by the irradiation. And this can be very useful for some kinds of radio-resistant cells which are now very difficult to treat with radiotherapy. And in this topic, hydrogenated nanodiamonds have shown some very good specification, and we are still working correlated to this radiosensitizing effect. We also studied these hydrogenated nanodiamonds as radicals emitters. Indeed, we have seen with our colleagues from the University Paris-Sud, Orsay, that when you make the irradiation with gamma or X-rays of these nanodiamonds in water, then you have the spontaneous overproduction of OH point radicals, but also solvated electrons. And this phenomenon only occurs for hydrogenated particles. You don't have at all this effect onto oxidized nanodiamonds. So this is a very important study that we led with these colleagues, and we are still working on it in order to better understand what is the origin of this overproduction of radicals and solvated electrons when you make the irradiation with X-rays of these nanodiamonds. And also correlated to that are the studies that are today conducted onto the use of nanodiamonds for photocatalysis and photoelectrocatalysis. Indeed, a few years ago it has been shown that bulk diamond can be a solid source of solvated electron. This is due to the position of its conductive band compared to the vacuum level, and it has been shown that bulk diamond can be very good catalyst for the reduction of CO2 into CO, but also for other kind of molecules which are very difficult to reduce. And this behavior has also been shown onto nanodiamonds, and this is the topic on which we are working this year, the use of the hydrogenated nanodiamonds towards photocatalysis and photoelectrocatalysis. And then to be able to use them as a functional material, then you have to assemble themselves. And we are working on nanocomposites, for instance, into PMMA. We are also working on the deposition onto substrate in order to have adhesive and robust layers of nanodiamonds. We also work on the adsorption and the building of some nanodiamond beads onto silica, and also we are still working onto the suspension, for instance, for photocatalysis. Okay, with this slide I will close this talk, and I will thank all my co-workers, especially Jean-Charles Arnaud, and also all the students involved in this topic, and all my collaborators from France or worldwide. Thank you for your attention.
Great. Okay, so next, last but not least, we have a talk from Cristina Sirtoage. I hope I'm pronouncing that right, from the Polytechnical University of Bucharest in Romania. And the talk is titled Electric Conductivity of Cadmium Selenide Zinc Sulfide Quantum Dots Dispersed in Liquid Crystals. Cristina, the floor is yours. Please go ahead and share your screen.
Yes, I will share it now. So is it okay? Can you hear me? Do you see the screen?
We can hear you and we can see the screen. Is there any way to maximize the presentation view?
Maximize, I don't know how.
The slideshow icon at the bottom right, where you have the zoom in and out slider.
Oh. No, I don't know what is this it? No, not this.
Might also be under a view at the top to go into presentation mode. If not, we can get going like this. This is okay.
Or you can use the video if you can show it better and I can answer questions.
Oh, I think we'll be okay. We'd rather hear from you live since you're here.
Yes, okay. I don't know. You don't see the slide enough because I see it on.
We see the slides. We see the slides, just not in presentation view, but we see your slides.
Oh, not in presentation. Okay, so it might be my new. Let's try new share. No, just a moment. Now this is better or just the same?
I think this will work. We just see your next slide also, but that's no problem. We can see it.
Okay. So as you mentioned, this is a work about the electric conductivity of cadmium selenide zinc sulfur quantum dots dispersed in liquid crystal. This work was developed together with my colleagues, Professor Emil Petrescu and Professor Alina Petrescu-Niță, both from the same university. And first of all, I would like to say a few words about quantum dots. I'm sure you all know about them and you heard about them. Just they are semiconducting nanocrystals with very small size, between 2 and 10 nanometers in diameter. So this would mean they have about 10 to 50 atoms. And they can convert an incoming spectrum of light into a different frequency of energy output. So they can be used for this purpose, but they can also be used because they are very, very small, and here the quantum effects are more visible. They're in other type of microparticles or even nanoparticles. And so far, they were studied for different applications, such as LED, light-emitting diodes, or photovoltaics, photodetectors, lasers, and also in medicine for imaging and therapy. So the applications are multiple. The interest is huge. And there are many topics in which they can be used and studied. We choose to analyze them in liquid crystal matrix. Liquid crystals, as you probably heard, because we all use liquid crystal in LCDs, they are liquid substances which present a crystalline order, just like in solid. So they have the benefit, to say, from both states. They are fluids, and we can disperse any type of nanoparticles in liquid crystal, and they can be organized by external field, or in some other cases by using a special type of preparation on the substrate used for this cell. And the most common preparation for the substrate of the cell are for planar alignment. Here, where in the first picture, when the cells have their long axis parallel with the substrate, when the liquid crystal cell, which are long molecules, are oriented with their long axis perpendicular to the support plate, we have homeotropic alignment. We have also a twisted alignment, which is sometimes used in LCDs when the long axis of the molecules are parallel with the support, but there is a 90-degree angle between the alignment on the down support comparing to the one on the upper support. So this is the twist configuration. And we can also have the hybrid configuration with a planar alignment on one plate and homeotropic alignment on the others. In each of these cells, we can insert different type of nanoparticles, and we can analyze their behavior by subjecting them to different external stimuli, such as an electric field, a magnetic, or a laser field. In this case, we used a planar alignment cell, and as a stimuli, an electric field. And the expected configuration would look something like this. When the quantum dot is inserted in a liquid crystal cell, the molecules of the liquid crystal will be attached on the dot surface, presenting a shape like this. So their long axis will be aligned with the radius of the quantum dot. But when we apply an electric field, the molecules will tend to align their long axis with the direction of the field, and the structure is distorted. This distortion may be observed by optical means when we have a laser crossing through the samples, but also by the change of electrical properties of this cell. Here is the experimental setup here we used. So this is the cell. The cell is connected to a power source with a voltmeter. From this power source, we shall apply an electric field on the cell, and for study we use a laser beam which crosses the sample and transfer the information to a photovoltaic cell. We also have to use a couple of crossed polarizers in front of the liquid crystal cell and behind it, because in this case we shall obtain similar intensity both from ordinary and extraordinary ray. We also have here an ampere meter to capture the intensity on the same cell. The cell was 15 micrometers thick cell. It was provided by Instec, and it was filled with a composite of pneumatic liquid crystal called 5Cb and a very small fraction of cadmium, selenium, zinc, sulfur quantum dots. Those quantum dots were dispersed in toluene, and in order to obtain homogeneous mixture, we have to use the solution just as it was, mix it with the pneumatic liquid crystal, and let it for 48 hours to be sure that all the toluene was evaporated. Then we could calculate the mass fraction of quantum dots used in this solution. For the precise type of quantum dots, we have 6 nanometer average size of the quantum dot, which leads to a fluorescence wavelength of 630 nanometers. After that, we recorded the intensity versus voltage plot for different temperatures in the pneumatic range. So only in that temperature range where the liquid crystal still presents its pneumatic order. These are the plot we obtain for each temperature recorded here. As we can observe here, there is a strong increase of the intensity after the voltage of, let's see, 10 volts here. It suggested us that there is a finite well, potential well there, because we consider that each quantum dot might be a potential well with the radio equal to the radio of the quantum dot. So in our case, 3 nanometers. And when the applied voltage is higher than 10 volts, the fact that such an increase of the current is observed made us assume that the electrons are passing by tunneling through this the wall of this well. We design the well, so we propose let's say the potential well of this form, the potential is 0 if the radius is smaller than R0, and alpha over R for larger values. Here alpha is a constant that will be determined from experimental data. In order to obtain the method to determine alpha and other constant, we have to assume to have a theoretical background. The first thing that we consider here is that the electron movement inside this well is not entirely free. So due to the interaction with the positive ions of the quantum dot atoms, the electron will have a different mass, which is called effective mass, and it's of course not equal to the rest mass of the electron that we all know. If there is no electric field applied on the sample, the electron energy on a certain direction, so we will not take into account the movement on OX, OY, and OZ axis. We shall only take it on OX, for example. So in this case, the energy is only thermal, and it can be written in this form, where Kb is the Boltzmann constant, T is the temperature. But when we apply an external field on this sample, the dot behaves like a vacuum cavity surrounded by a polarized dielectric, which is a liquid crystal. And we have an additional energy, which we expressed in this form. So it's a function of the electric charge, the fraction on the electric charge on a parameter if, depending on the dielectric permittivity of the liquid crystal, on the quantum dot diameter, the applied voltage, and of course on the cell thickness. The total energy is the sum of the two previous values. So we have the thermal energy term and the electric component energy term. According to Landau theory, the transmission factor of the electron to this barrier can be written in this form. So it's proportional to this expression, where the function of R on the applied field, which appears here on the upper term of the integral, can be determined from this relation connecting the energy and the design potential well from the beginning. Thus, by taking all this equation into account, we managed to obtain a theoretical expression for the intensity. So for the intensity of the current on the sample, and this expression has this form. It's a complicated expression. Depending on alpha term that we intend to calculate it here, the effective mass of the electron, electric charge, and the quantum dot dimensions. Using this function, we used to fit the data, the experimental data obtained. Here I put 4 examples at 4 different temperatures, trying to choose them to cover the entire nematic range. As you can see, the theoretical function fits the data very, very well. And we can also calculate some values from this function and from experimental data. We calculated the ratio between the effective mass of the electron and the rest mass of the electron. As you can see, the values are quite close. So the results are reasonable in our opinion. And we could also determine the parameter alpha over R0. And from this parameter, by knowing the radius of the quantum dot, we could find the alpha parameter from our theoretical experiment, our theoretical function, and they are also very close. And here, from this function, from this expression, we can determine these F parameters. A, B, C here are just, let's see, intermediate results using from this relationship from above. These are the results we obtain for different temperatures in the nematic range. And in conclusion, we were able to propose a theoretical model for the intensity versus voltage dependence in composite of quantum dot and nematic liquid crystals. In this kind of experiment, we pointed they are indeed quantum effects, and we can use this effect and this mixture for other composite and other nanomaterials that can be used by engineers in different fields. A tunneling effect was observed from experimental data in this kind of composite, so we assume they can be suitable for electronic application. And as a final observation, this quantum dot insertion affect the field inside the liquid crystal cell for very high voltages, much above the Friedrichs transition threshold, so much above the voltage that allows the molecule to change their orientation, which means that they can be used for optical effects without affecting the switch on or switch off voltage, which is used in typical LCD. These are the conclusions of our research, some more references used for
Christina, I think unfortunately we okay.
And
Great.
thank you for your attention. Yes, thank you. Sorry if I exceeded the time. Thank you so much.
That's okay. Thank you very much. That was a very nice combination of experiment and modeling. Thank you for giving the talk. With that, we are at the end of our session. I'd like to sincerely thank all the speakers for really wonderful science and for doing their best to stick to the time, and enjoy the rest of your conference. This session is now formally ended. You're welcome to leave or stay in here.
Okay, thank you. Have a nice day.
You too.